Pipework is the most common critical path of oil and gas projects. This is not surprising given the number of activities involved and the time they take, from welding through non-destructive examination up to piping completion and hydrotest. Piping discipline groups a number of specialties, two of which we have already covered in dedicated modules, plant layout and materials and corrosion. Therefore, in this module, we will look at the remaining disciplines, which are piping installation, in charge of the routing of lines, piping calculation and supports, in charge of the calculation to confirm the routing that has been designed by piping installation and to define the types of supports required for the lines, and then piping and materials, in charge of specifying and ordering all piping materials. Let's start with piping installation. Piping routing activities start once the equipment positions have been fixed, i.e., once the unit plot plan has been issued. Piping uses this drawing as a background to draw each and every line as a single line. This is called the line diagram. It shows the routes of all the lines, and therefore it is sometimes called the piping routing drawing. As each pipe is shown as one line without taking into account its diameter, these drawings are called line diagrams. They show the density of lines in each area. They also allow to confirm that the unit plot plan is sound, that there are not too many up and down on the pipe rack between equipment, and the distances of pipes have been minimized. They also allow to split the work of piping design among various piping designers. Each piping designer is allocated one area to perform what is called piping studies and issue piping layouts for this particular area. Let's review which are the requirements that are taken into account while doing these piping studies. First of all, the process requirements. These are shown on the PNIDs. They include requirements for the proper flow of fluids inside the lines, such as sloping, requirement for one line to be sloped, or to have no pocket to prevent accumulation of liquids in the low points of gas lines, for instance, as well as some indications for minimum distance, and so on. Pressure safety relief valves or depressurization valves, for instance, are located at high point above the equipment they protect and above the flare header to which they discharge. All these indications are shown by process on the PNIDs. Other requirements that are taken into account while doing the piping studies include the flexibility of the lines. The layout of lines must provide enough flexibility so that the line can deform when subject to thermal expansion without being subject to excessive stress or without subjecting the equipment nozzles it connects to excessive forces. Although these will be checked in detail by the piping calculation group, at the stage of piping studies, a flexible layout must be proposed by the piping designer based on experience. It will later on, as I said, be confirmed by calculation, but space must be allocated and adequate expansion loops, as the one shown here, for example, for the line connecting the bottom of the column to the pump must be provided. Piping studies will also consider access for the operator to manifolds, such as the one shown here, the valves on the pump suction and discharge lines. Access to instruments as well, straight lengths for instruments such as flow meters. All this will be considered while doing the piping layout. Once these piping studies are completed, the piping layout drawing, such as the one shown here, is issued. This is an internal drawing issued by the piping designer to other disciplines, including, as I said, the piping support engineer for the calculation of the line. These drawings are also the starting point for the detailed modeling of the line in the 3D model. Modeling of lines in 3D models are done from a catalog, picking the various piping items from this catalog. Piping items are standardized. That means that their dimensions are defined by codes, so they are the same from one project to the other, so that generic catalogs can be prepared and can be used. However, some items are not standardized, and these include control valves, as well as inline instruments, also pressure safety relief valves. So for these items, the dimensions must be provided by the vendor and must be input in the system. Once a sufficient number of lines have been modeled in the 3D model, typically once 60% of them and then 90% of them have been modeled, a review of the 3D model is conducted with the client. These reviews mainly look at the access of the operator to all items, equipment, valves, instruments. They also check that there is enough space around equipment for the maintenance. Once the 90% model review is completed and comments are incorporated, piping drawings can be issued for construction. These drawings are the piping isometric drawings. They are extracted from the 3D model. They show the line geometry as well as a list of all piping materials required to fabricate and erect the line. They also must show all information required during the fabrication of the line, including types and extent of non-destructive examination, if any post-well heat treatment must be done, the applicable paint code. Isometrics are duly checked prior to their issue for construction, including compliance with IFC PNIDs, position of instruments and interface between instruments and piping, that the line is properly supported as well. Isometric drawings are used for piping prefabrication. Another type of drawing is issued for piping erection, the piping general arrangement drawings. It must be said that these drawings tend to no longer being issued today, as extracts are made instead from the 3D model. These drawings are nevertheless issued at the end of the job to serve as future reference for the plant owner, as they show the complete equipment environment. The piping installation work process I've just described can be summarized in a flow sheet. One thing is missing from this flow sheet: piping stress analysis. In other words, piping calculations. I will now describe this activity and we will add it to this flowsheet. Do you know by how much does a 10-meter long line expand when its temperature raises to 200 degrees? It expands by 20 millimeters. Therefore, one understands that direct connection between the nozzle of the column and the nozzle of the pump cannot be done. Indeed, when the line expands, it would lead to excessive effort on the pump nozzle, leading itself to misalignment between the driver and the pump, which would ruin the pump. Therefore, enough flexibility must be provided in the line so that it will absorb its thermal expansion and not bring excessive efforts on the nozzles of the pump and the equipment. This flexibility is achieved by adding an expansion loop. For the case of a pump, this is so critical that the line is subject to a detailed calculation called stress analysis. The piping support engineer inputs the geometry of the line as well as the position and function of the supports it proposes for this line in a finite element calculation software. The software calculates, based on the line maximum operating temperature and pressure, the stress in the various parts of the line, and also at connections to equipment nozzles. And then the piping support engineer checks that the stress level in any part of the line is below the maximum stress level acceptable for the material of construction of this line, and that the maximum efforts at equipment nozzles is not exceeded, which validates the routing and supporting of the line. The stress analysis also provides the load on the piping supports that shall be considered by civil in the design of the supporting steel structure. So a drawing similar than the one shown here shows the additional steel members and the loads to be considered by civil in the design of the steel structure. Not all lines are subject to a detailed calculation. A classification is made to identify which lines shall be subject to a detailed calculation, which lines shall be subject to a simplified calculation, and which lines will not require any calculation but will just be routed and supported as per usual practice. The criteria depends on the line diameter and wall thickness, because the larger the diameter and the higher the wall thickness, the less flexible is the line. Of the temperature change to which the line is subject, and the type of equipment the line connects. For instance, fragile equipment such as rotating equipment makes a line more likely to be a critical line. So charts like this one identify which lines are level 3 lines to be calculated by detailed calculation, level 2 lines, or level 1 lines. Now that we have seen the types of calculations done for lines, let's focus on supports and see what type of drawings are produced for the supports. First of all, as part of the support needs to be installed during the line prefabrication, which is the pipe shoe that is welded to the pipe itself, the type and position of supports must be indicated on the piping isometric. Nevertheless, the piping isometric does not show the detailed drawing of the support. This is shown on a dedicated drawing. Most supports have a standard design for which standard drawings are issued. A few supports have a unique design for which special support drawings, individual drawings, are issued. All information related to pipe supports is shown on the pipe support book. It indicates for each support the reference of the standard drawing, together with any additional dimensional information required for fabrication, or the reference to the special pipe support drawing. A few special supports require specific material such as spring supports or hangers, rigid struts. The material requisition for this special support equipment is issued by the stress and support discipline. Now that we have seen the work of the piping stress and support engineer, let's see how it integrates with the piping installation work sequence. First of all, once the piping layout has been done and a proposed routing has been chosen for a line, it is checked by the piping stress analysis. In case any changes are required, they are fed back in the 3D model. Finally, before any isometric is issued for construction, it is checked by stress for compliance with the calculation note, in particular the position of supports. There is a large variety of piping materials, depending on types of items such as tees, elbows, flanges, materials of construction, as well as wall thickness. In order to reduce the variety of piping materials at site, a standardization is made. This is done by grouping different services shown on the process fluids list in classes of identical piping materials called piping classes. For each piping class, a detailed piping material class specification is issued. The piping material class specification shows for each type of piping item and for each diameter the required material by reference to an international standard, usually ASTM, the required dimensions, also by reference to an international standard, the type of manufacturing, as well as the wall thickness. The wall thickness is calculated applying the formula of the applied piping design code, usually ASME B31.3. The formula is applied for the pressure and temperature limits of the piping class and for the selected grade of steel. The piping material class specification also provides the specification of manual valves of the different types, such as ball valves, gate valves, check valves, globe valves. The specification is usually made by means of specifying a design and construction, inspection and testing standard, such as API 6D. This standard also defines the dimensions, in particular the inline dimension of the valve, which enables the piping isometric drawings to be issued without waiting for vendor drawings. The specification of the valves in the piping material class specification indicates the type of construction of the valve, which impacts the easiness of its maintenance, the materials of the body, of the trim, that is the moving part of the valve, as well as the seats and the seals, which determine the tightness of the valve. Piping materials are required at site at the same time as construction drawings. Piping materials require anything from 2 months to 8 months from order to ex-works delivery. Therefore, they cannot be ordered on the basis of the bill of material shown on the construction drawing, on the isometric drawings. They have to be ordered much earlier. Therefore, one must produce an early list of piping materials. An inventory of these materials, called a material takeoff, must be done from the non-final P&IDs and the non-final piping drawings. Such bill of materials will be done from the second revision of the P&IDs, the issued for design P&IDs, which is not the final issued for construction revision, and from the piping layout drawings, because the piping isometric drawings are not available. Once the piping isometric drawings will be issued, a balance will be made for each line between the final bill of materials shown on the isometric and the materials that have been ordered for the corresponding line, and additional materials, if any, will be ordered at this stage. In fact, an even earlier estimate of required quantities is required to issue inquiries to potential piping materials vendors. This earlier estimate, which is required 2 to 3 months before the purchase order, in order to have time to receive the bids from the vendors and select the most competitive vendor, is done from the first issue of the P&IDs, as well as from the piping line diagrams. This synoptic shows the 3 revisions of the piping materials requisitions. The first one for inquiry, the second one for order, where quantities are committed, and the third one and next ones for ordering additional materials or top-ups. This final synoptic shows the integrated piping work process with piping installation, stress and support, and piping materials. Thank you for your attention. Goodbye.